Okay, good morning. Let's have a class. And let's continue to talk about this section, especially calculating the ATPs, raw aerobic respiration. Then we are going to the genetics class. Okay, this is what we already talked about, the glycolysis, and we're going to go back to review it one more time. So this is what we have, is glucose going through this branch reaction and will generate a pyruvate. And then this pyruvate could go in the anaerobic environments going through fermentation. And then they could be in aerobic environments going through TCA cycle. And we already talked about is this top here, glycolysis, and this fermentation. And we know the fermentation only generated 2 ATPs, and that is coupled from glycolysis. And we go all the detail, talk about the chemical structures, chemical names, and how they generate ATPs, all those things. So we want to first directly jump to here to talk about TCA cycle. We already talked about these oxidative phosphorylation and electron transport chain, chemosmosis we already mentioned, so we're going to directly jump to the TCA cycle. Okay. Some of you already taken the class before. It certainly helps, like I mentioned, but in this class, we will do a little bit different. So TCA cycle, I'll just write it here. There are different names, but all the same. Okay. TCA cycle, tricarboxylic acids cycle. Tricarboxylic acid cycle. And we also, some people call it a citric acid cycle. Same thing. Or Krebs cycle. That's by the scientist who is being founded this. Okay? So you already know it's a circle, so let's talk about that. It's all started from pyruvate. So we have this whole board, we're going to talk about that. It's all coming from pyruvate. What does pyruvate look like? CH3, CHCOOH. Pyruvate, first of all, needs going through a transition step. This transition step is right here. And here, it will become acetyl-CoA. So what's that? CH3. This is too so slow. Let's talk a little bit talk. I'm not that tall, but I'm trying best. COOH. This is pyruvate. Then going through a transition step will become CH3COO SCOA. That's become acetyl-CoA. Okay, we call it acetyl-CoA. Now, very important here. What is the key here? You look at here. There is NAD plus reduced to NADH2. That is the key point. Because in here, we basically care about is where there is an energy generated, which is ATP generated. So that's a key point. Now, acetyl-CoA, this is SCOA. You know it's a very long chemical structure. This is just an acronym, so we always call it acetyl-CoA. Now we go this big circle. Now always remember, when we talk about the structure, chemical, sometimes you're feeling about it's difficult to do. Yes, it's difficult, it's complicated. But since it's called citric acid cycle, you at least need to know or remember what is citric acid. Because it's all coming from there. So let's go talk about that. What is citric acid? COOH, CH2, then go here, COH, COOH, CH2, COOH. This is citric acid. And it is actually not difficult to memorization. Because you see 3COOH right at top, middle, and the bottom CH2 is there, and hydroxy bonds is on the center carbon. So it looks like it's symmetric, it's easy to understand. Not really difficult. Now, next step. In your biochemistry class, it will go to cis-ascorbic acids. Because you talk about human beings, animals, and the fungi, which is for eukaryotes. Here, we use an example, it's for E. coli, it's for prokaryotes. So we skip those steps. We directly go to isocitric acid. So what is that? Isocitric acid. Since it's called iso, which means they're going to make some change of the citric acid, but that change will be very minimal. In other words, the structure basically looks fine, looks the same, and the molecular amount is the same, is only a little bit of place moved. So what are they moved? COOH, same, CH2 the same. Go here, instead of you have, and then instead you have OH, you have H. Then go here, you have OH and CH2. And then you have COOH. So that is isocitric acids. Now, if you forgot about it, let's say you forgot about it, you can come here to do the double check, what it looks like. Yes. So what's the point here? Hydroxy group moves down. And this proton, or this is a hydrogen, moves up a little bit. Okay, that's called isocitric acid. This is nothing happened. Isomerization. Now, why this wants to do that? These type of bonds, make sure it's a little bit weak, and these things here, look at so many COOH. This tells you something's going to happen, they're going to go. Because too many. If you have some more feeling about that. So next one, what happened is absolutely is the carbon dioxide is going to go, and happen is NAD plus reduced to NADH2 will become a chemical is called alpha ketoglutarate. C and COO plus. Sometimes you say COH is fine. So this guy is alpha ketoglutarate. This is a very magical stuff. If you know about that, that's going to go lipids, oxidation cycle, and the protein synthesis, all kinds of things. This is a magical stuff. Okay, now, you see here, not stable. Okay, so what you do? Goes here, will become COOH, CH2, CH2, C connected with SCOA. This SCOA going to comes out. And what happened again is NAD reduced to NADH2. Therefore, this guy, and also lose one carbon dioxide. This guy goes succinyl-CoA. Okay, then also it's succinyl-CoA goes here. That's very easy to lose. So you go here, COOH, CH2, CH2, then become COOH. This is succinate. Oh, we call it a succinate. Don't forget about it. Here what happened is one GDP will be generated GTP. So it is not an ATP. It's GTP because this is an alternative energy resource that could be used very specific in the TC cycle. Okay, this is source leader comes up. Once the source leader comes up, you see the right middle here. When you see H2 there, right in the middle, so it's symmetric. That tells you something will be happening. Okay, what happened? You go up, will become COOH, C double bonds, COOH. That's Fuma rate. Now there's a question. Lose hydrogen, lose proton, where do you go? They need some places to go, is that right? So here what will happen is FAD reduced to FADH2, forming adenine dinucleotides. This is nicotinic adenine dinucleotide. This happens. This is the key. Okay, we want to remember. Okay, Fuma rate generate. Double bonds in the middle, not stable. We need to put them stable. So what we do? The water gonna put them back. So you go water, put them back, then it becomes COOH, CHOH, H, CH2, COOH. What is this guy? Malate. Okay, do you like beer? You like beer? Malate gases, that's what it comes from. The malate. Okay, once you have here, this is unstable again. Hydroxy bonds right in the middle, so symmetric, something gonna happen. So what we go? Here, you're gonna lose the you're gonna lose H, which means H2, which means you're gonna lose proton again. Now what happens? NAD will reduce to NADH2. That's transferred to NAD plus. So become COOH, CH2, and COOH. And this goes back. What's the last one? Oxaloacetate. And right in the middle, citric acid cycle. Okay, that's the citric acid cycle. Now what we care about. This is not a biochemistry class. We don't care about these chemicals. That's your biochemistry major teacher's job. What we care about is energy generated. How many energy generated? How many ATP generated? So, here we're going to set up a rule for you. Okay? We learned about that. NAD plus reduced to NADH2. Now, of course, there is a two proton, two hydrogen there. And we also going to happen is FAD becomes FADH2. Okay, how many ATP going to generate? When I was students, it is easy. This is going to generate 3 ATPs. And the bottom one is 2 ATPs. That's an old calculation. In your textbook right now, or the biochemistry textbook, in the recent 5 to 10 years, because we considering the ratio between oxygen and phosphate, so the top one becomes 2.5 ATPs, and the bottom one becomes 1.5 ATPs. And in this class, in order to make the calculation a little bit easy, I would suggest you to use this guy. But if you want to using the complicated one, that's okay. I don't mind. I would use the 3 and 2. It's easy. Okay, it's not confused because this calculation makes it easy. It doesn't make much difference. So let's see. Citric acid cycle, how many ATP generates? Where are we going to find? Obviously, we want to find where is NAD plus reduced to NADH2 and FAD plus reduced to FADH2. So we're going to circle it. Where are they? there is one happened in the transition step. There is a one happened right here, generate alpha ketoglutarate. There is another one happened is succinyl CoA generate right here. And there's another one happened is very later malate to become oxaloacetate. Okay, we find that there is a four place happened. 1, 2, 3, 4. Four place happened is NAD reduced to NADH2. So let's do the calculation. It's 3 ATPs multiplied by 4 equals 12 ATPs. Okay, where is FAD reduced to FADH2? We want that one. Circle right here. That's the place happening. So you can do the same thing. That is 2 ATPs multiplied by 1 equals 2 ATPs. And do not forget, there is another magic stuff here, is the GTP generator. And we think this GTP is equivalent to ATP. So right here. Okay? This GTP is equivalent to ATP. Now we're going to talk about AMG real quick. So don't forget, there is a 1 ATP generator. So how many total for one cycle? Add up together, use older rule, is 15 ATPs. And do not forget, the TCA cycle is a 2 cycle. Because the pyruvate is from a branch reaction, there are actually 2 TCA cycles. So you have to multiply them by 2. So multiply them by 2 cycles. Equals what? 30 ATPs. Now, here is my question. With these type of 30 ATPs, how many coming from oxidative phosphorylation? How many they come from substrate level phosphorylation? Now, even if you don't know, it's very simple. Whenever you see the places NAD reduced to NADH2, FAD plus reduced to FADH2, that is generate ATP is going through oxidative phosphorylation. And when you see here, have a GDP reduced to the GTP, this is substrate level phosphorylation. Now, oxidative phosphorylation, what's the principle behind that? Chemosis. Is that right? That's what we talk about. Peter Mitchell's principle, the big research right here, win the Nobel Prize later on. That's how many they generate. And that's the story behind that. The proton multiphos accumulated the potential energy. When they accumulate too much, you're going to put them back and activate ATP synthesis, generate ATP, and coupled with flagella rotation. That's chemosmosis. Why I want to use this one in this class? Because it's used bacteria. Actually, it's somewhat similar to Proteus vulgarius as an example. And he also used E. coli as an example. But the flagella rotated is not that obvious. Okay? So this is something we'll talk about. So finished here. Then there is a question. How many ATPs generate through aerobic respiration? Therefore, we have a slides right here. Okay, we already calculated this part. This section is citric acids, including the transition step at the top. encoding the transition state. What we are missing is glycolysis part. Okay, how many ATP generated? Lots of people say 2. Okay, let's do it. So I draw it with the one. Aerobic. Okay, let's figure out how many ATP there are. At the beginning of this branch, they hydrolyze, they use the 2 ATPs. We call it an investment area. We know that. Okay, you can go back to see the procedure again. How about here? They generate the ATPs. Okay? Where they come from? Phosphoenolpyruvate become pyruvate. There is a 1 ATP generated in one branch. Another place is what happened. Yes, 1,3-biphosphoglyrate. When they become 3-phosphoglycerate, there is 1 ADP generate becomes ATP. But do not forget, before that, glyceroldehyde 3 phosphates become 1,3-biphosphoglycerate. I said that phosphates is coming from 3 available and coupled with NAD reduced to NADH2. And this relying on enzyme called hydrogenase, dehydrogenase. If this involved in the aerobic respiration, this guy go to electron transport chain. So how many ATP generated there? Is 3 ATPs. So how many generated here? That is 1, that is 1, that is 3. So that is 3 plus 1 and 1 for one branch. We have 2, generate 10 ATPs. Remember hydrolyze 2 here. So minus 2 at the top. If you add them together, equals 8 ATPs. And these 2 you combine, 30 add 8 equals 38 ATPs. But here is the thing. On Tuesday, you say, going through glycolysis only generate 2 ATPs. That's what you learned. The glycolysis only generate 2 ATPs. How come here you come up with 8 ATPs? Because when we talk about the glycolysis, that's only a closed cycle. That's not related to the electron transport chain. When we only talk about the glycolysis, they actually coupled with fermentation. So this guy is not going through electron transport chain, which means there is no place to generate the chemosmosis. Therefore, if only glycolysis cycle without involved in the aerobic respiration, it's only 2 ATP generated. Okay? So here's what we want to say. If only glycolysis without involved in aerobic respiration, only 2 ATPs. This is a quotation mark, you need to take a note. But here, if it's involved in aerobic respiration, when you see here, it's going through electron transport chain, it's generating another 6 ATPs. 3 for one branch, 6 as a total. Remember, 38 ATPs is using all the rules, and this is for bacteria. But how about fungi? How many ATP generate? 36 ATPs. I just tell you a story. I just tell you the result. It's 36 ATPs. Where is that 2 ATP goes? Passing through the mitochondrial barrier. Like you go to a park, you need to pay the ticket. That $2 is ticket. Very simple. Oh well, you biochemistry textbook will have another calculation to go all the complicated stuff. But I tell you, in my class, it's easy. That $2 is going from ticket passing through mitochondrial barrier, we just said. Like a gate. Okay? That is a process, what we talk about TCA cycle, aerobic respiration. I will take a separate picture here, and then I'll put on the eCampus. For some of you have not taken the biochemistry test, and then I will be put on the eCampus for you to study. And on Thursday, in the lab section, on the blackboard, I will be redraw this again. And also videotape to put on the eCampus, you can review it. Okay, now, some of you ask for extra points of the exam. We do offer you a lot. What are we going to offer you? Every single chemical, the name and the structure of the TCA cycle. Same as the glycolysis. The name 0.5 points, structure 1 point. Okay? So every name 0.5 points, structure 1 point. So that's simple. If you don't want to get enough extra points, you said I want a little bit, just draw the name. Okay? Okay, now somebody going to ask me, I don't want extra points. I already did it very well. So what I should do? Okay, this is the first 3 years when I was here teaching the class. I don't go through this 3 cycle because there's 1 year, there's one student come to me said, Dr. Shen, you don't be taking it granted for all of us has already know biochemistry. Some of you doesn't even know about it. So I have another easy way for you to do. If you don't want any extra points, you said already very good. Then in